Okay, well, thank you, Angela. Thank you for the introduction, and thanks for the invitation to come and talk to you today, and also for organising this series. The short title of this talk, of my presentation today is "What is Generalized Method of Moments?" And there's a rather longer title that was advertised that says "An Introduction to a Popular Method of Statistical Estimation in Econometrics." And I thought that to help particularly non-economists to understand why the method has become so popular, it might be useful just to say a few words about the form that econometric analysis often takes. Well, econometrics, I'm sure you know, is the use of statistical methods to analyze economic data. And in an econometric analysis, it begins with some economic phenomena that's of interest to us, that we want to analyze. And first reaction is, of course, to turn to economic theory to see what insights that it can offer. Okay, now, economic theory these days postulates an explanation for economic phenomena in terms of a set of mathematical equations. Now, these mathematical equations involve two types of quantity. There's economic variables that naturally arise in the context that we're looking at, and also certain constants that we're referred to as parameters that reflect aspects of the economic environment. Maybe something to do with tastes of individuals or technologies available to firms. Okay. Now, in the context of this, the economic model we're working with, interpretation of these parameters is typically well understood. Okay? But we don't know the specific value that they take. And if we're going to use the model to perform an inference about our original question, we need to come up with values for these parameters. Okay? And it's here that we turn to statistical methods and use the combine the observed economic data to come up with estimates of these parameters. Now, when we come to this stage, there are a number of methods that are available to us for estimating these parameters. And in choosing between them, an important consideration is that we'd like to adopt a method whose implementation does not require the imposition of additional restrictions to the statistical behavior of the economic variables beyond those that are implied by the economic model. And the reasoning for that is as follows. If it turns out that just for the purpose of getting these estimates, we have to propose additional restrictions or make additional assumptions, and they turn out to be unjustified by economic theory or inappropriate for our data, then we run the risk that their invalidity will undermine all our subsequent inferences about the phenomena of interest to us. So what we'd like to do is to use a method of statistical estimation that fits well with exactly the kind of information that we're getting out of our economic models. What form does that information take? Well, very often these days, the form of the restrictions that are implied by economic theory take the form of what we refer to as population moment conditions. Okay? And this is where Generalized Method of Moments is going to come in, as the name already suggests. It provides a statistical method that enables us to combine observed economic data with the information in these population moment conditions to come up with estimates of these unknown parameters of this economic model. When we have those estimates, then we can go on to perform inference about the basic question that's of interest to us. So that's the reason for the popularity of the method, is that it's very well tailored to exactly the kind of information that we're getting out of our economic models. Now, to be more specific about what the method involves, first thing we need to do is to say what we mean exactly by a population moment condition, because obviously that's going to be a crucial quantity in the whole discussion. Now, the term of a population moment condition, which you're well aware, has been around in statistics for a long time, going back at least to the early to mid-19th century, where it was, I believe, introduced by Adolphe Quetelet, if I pronounced that correctly. And he was interested in specifically what we would now call an Rth population moment, which we would write these days, as on the slide, as an expected value. So if we have a random variable v, its Rth population moment is the expected value of v raised to the power r. Think of that as just a population average of v. This notion was inspired by sort of ideas of centre of gravity in physics. And of course, as you'll be well aware, that these moments reveal important aspects of a distribution, such as the first population moment is just the population mean. The first two tell us something, give us the variance of the distribution. Now, in the context that we're working here, I want to adopt a broader definition of a population moment. Okay? And we're going to be, here, what I'm going to mean by the phrase a population moment is where we have a function of the observed data v and the parameter theta, whose expectation, as I have it here, is this will be the population moment, and the population moment condition is if that expectation is equal to 0. So that it's more general. This could be any function here involving the data and the parameter. It's a population quantity, and of course, as we come to operationalize GMM, we're going to need sample analogues and refer to the sample moment just as being this quantity here, which is just replacing the population average by the sample average. Okay. So that's what where we're going to use the term population moment condition in the context of this talk. And so, armed with that, we can now start to flesh out what we mean by a generalized method of moments estimation. And to motivate the form that it takes, I thought it might be useful just to go back and myself with the structure of a method of moments estimator, which we're familiar with in many branches of statistics. This, of course, is due to the work of Carl Pearson back in the late 19th century. And the form of this will help us to motivate the subsequent form of a generalized method of moments estimation. Now, to set it up, just a brief reminder of the context that Pearson was working with. He, like a number of other people at that time, were interested in coming up with mathematical representations for probability distributions for various phenomena. And he'd come up with the Pearson family of distributions. It was a very flexible mathematical representation. And depending on which member of this family you chose, you would get a very different shape for the distribution. It could be a normal, could be a beta distribution, with many others. Okay. Now, the choice that you made out of this family was actually determined within this general expression by a parameter vector, just like the parameters we were referring to in economic models. A set of constants, and if the particular values of those constants gave us a particular type of distribution. Now, the problem that Pearson faced then was how to come up with what's the appropriate member of the family for a particular data set that you have to hand, or just expressing it in alternative terms, how to estimate the parameter vector that indexed this general family of distributions, so that you would know which one was most suitable for the data in hand. And to illustrate how he did it, we'll just take an example. Okay. Okay, a particular member of this family was the normal distribution, and to keep it simple, we'll suppose that we don't know the mean, that's what we wish to estimate, but we happen to know that the variance is equal to 1. One of Pearson's key insights, was to recognize that if you worked out the first population moment of this random variable, it would equal this unknown quantity, theta, and thus he could construct what we were referring to as a population moment condition involving the data and the parameter. His second insight was to recognize that you could then turn this into a vehicle for coming up with an estimate of the theta, this value theta, from the data simply by replacing the population moment by the sample moment and then solving the implied equation to get an estimate for theta, as is done on the slide here. And of course, in this case, we get the very familiar result that our estimate of the population mean is just the sample mean. Very powerful idea, very intuitive idea, but one not without its weaknesses. And a number have been discussed, but there's one that's particularly relevant to our discussion here. Okay, suppose that our estimation there was done on the information in the first moment. We could recognize that other moments would also contain information about this unknown mean. For instance, the second moment, given that we had assumed the variance to be 1, would imply this population moment condition, which also would contain some information about our unknown theta. Or suppose, so I'd like to base my estimation now on not only that first moment, but on the first and the second moment. If I do that, I now end up following Pearson's idea with 2 sets of equations that I need to solve. But crucially, I've got 2 equations in one unknown, And in general, there's not going to be an exact solution for those equations. So the method of moments approach is going to break down. And that exactly motivates what we're going to refer to as generalized method of moments. It's going to provide a way of circumventing that problem to allow you to get estimates of theta based on, in this case, based on more than one moment condition. So we'll first give the sort of mathematical definition and then explain what lies behind it. So first I should say that it was introduced into the econometrics literature by Lars Hansen in 1982. Okay, so it's a way of exploiting the information in our general form for a population moment condition. It's written on the slide here. And our GMM estimator is defined to be the value of theta that minimizes this quantity, qt of theta. And observe that qt of theta is just a quadratic form in the sample moment. Okay, and sitting in the center of that quadratic form is a matrix, W sub t, that we'll refer to as the weighting matrix. Okay, well now let's just tease out what's going on there. And to do that, some dimensions are useful here. We'll let the dimension of f, which is the number of moment conditions, be q, and the dimension of theta, the number of unknowns parameters to be estimated, be p. Now, if q is equal to p, we have exactly the same number of moment conditions as parameters, then in fact what was written on the last slide will actually just boil down to method of moments based on the original population moment condition. For the simple reason that this original information constitutes p equations in p unknowns, and a method of moments then principle will apply, and generalized method of moments will reproduce that solution given the way that the estimator is defined. However, if we have q greater than p, in other words, we've got more population moment conditions than parameters, a situation in which we know that in general there won't be a value of theta that solves the sample moment conditions and sets them exactly equal to 0, what GMM estimation is doing is coming up with an estimator of theta and defining that to be the value that's closest to solving those set of equations. Okay? So rather than being an exact solution, it's the value that's closest to solving the moment conditions. And the notion of closeness here is, of course, defined relative to this quantity qt, which represents a measure of how far the sample moment is from 0 for different values of theta. And for this exercise to make sense, of course, this measure has to satisfy certain restrictions, not least of which is that it must be non-negative. And so if we were going back to our earlier little example that Pearson was working on, then to get our estimate based on the first two moments that we couldn't do with method of moments, to achieve that with generalized method of moments, I just need to define f to be this two-dimensional vector. Here's the information from the first moment on top and the information from the second moment below. Okay, and then it'll come up with an estimate. Before going on to elaborate on the method, it might be useful just to touch on a couple of other methods of estimation statistics that are very closely related to this. And chief among those, I think, are method of minimum chi-squared and instrumental variables. Method of minimum chi-squared bears a lot of similarities to generalized method of moments. It was originally proposed by Neyman and Pearson back in 1928. This is Egon Pearson, Carl's son. And they're working in the context of a rather specific problem to do with parameter estimation in a goodness of fit example. And although they didn't think or didn't work explicitly in terms of population moment conditions, we can, with hindsight, go back and look at what they did and recognize that effectively they were solving the problem of how to estimate parameters from more moment conditions than you had parameters. Now, they may not have recognized it explicitly, but certainly later Neyman came on to think about there was more generality here, and he had work in the 40s and the 50s in the math stat literature that certainly indicates the potential of the method in the generality. But for whatever reason, it doesn't appear to have developed into quite the full-blown framework that generalized method of moments has become. And it's certainly true to say that at that time, it doesn't seem to have impacted on econometrics, certainly in the 40s and 50s as a method. Instrumental variables, though, that does have more direct influence, perhaps. That's something that was developed within the context of econometrics. And in fact, we can demonstrate that an instrumental variable estimation is a special case of generalized method of moments estimation. And so in some way, the kind of theoretical arguments that were developed for instrumental variable estimators are in actual precursors to the analogous arguments in the GMM framework. So similar kind of structures were coming through in the analysis, although in a much more general setting. Okay. Two examples just to illustrate the kind of things that econometricians have used this method to analyze. And just to give you examples of the types of moment conditions that arise in economic analysis. And one is returns to education example, a paper by Angus and Kruger in the Quarterly Journal of Economics. Here there's a model where we're interested in looking at the relationship between the number of years of education and the subsequent earning potential of individuals. And the particular angle that they had on this was that they were interested in the impact of compulsory schooling laws in the United States, trying to work out the economic returns for individuals that have been forced to stay in school to a particular age. Okay? So the parameter that's of interest to us here is this theta subscript d, which would be like the semi-elasticity, which tells us 100 times that tells us the percentage change in the log wage. The percentage change in the wage for the for a change in education. It's a linear regression model, and our first instincts might be just to estimate that by ordinary least squares, but that would not be such a good idea here because one of the explanatory variables, and particularly the one we're interested in, education, is likely going to be correlated with the error in this equation due to something such as omitted variables such as capturing the innate ability of the individual, which would likely affect both the amount of education they have and their subsequent wage. So what Angus and Kruger did was so least squares won't do, but they were using the structure of the schooling laws that were around in the United States at that time. They were able to argue that the following population moment condition would hold, which was said that the error term to that wage equation will be uncorrelated with a vector of variables that would include both the controls and, most crucially, the dummy variables indicating the quarter of the year in which the individual had been born. So it gives an example of how a moment condition arises in that setting. That moment condition can then be turned into used as a basis for a generalized method of moments estimation of the parameters of interest to us in that model. A very different setting is one from finance in sort of asset pricing. Here the problem that we're interested in is trying to model the movements of assets, financial assets over time. One popular approach to doing that is using the so-called consumption-based asset pricing model. So you're relating the movements of the assets to the consumption and investment decisions of what's called a representative agent. And that agent is making consumption and investment decisions to maximize what economists call their future lifetime expected discounted utility. In other words, how good they're going to feel for the rest of their life and how they feel about that today. Okay? And they make those decisions dependent on an information set, the information that they have available to them. But as they make decisions, they can't just choose options to make themselves feel good. In every period, we've got to satisfy a budget constraint that means that the individual, what this individual spends must be equal to the income that the individual receives. Okay, so that makes these decisions. And in this particular example, how good you feel about yourself depends purely on your level of consumption, which has been given a particular functional form here. And the asset that you invest in brings a return in the following period. Simplifies the structure. Now, so within this setting, there are two parameters that would be of interest to us, gamma and delta. Gamma was in the utility function. It tells us about attitudes to risk. Delta is a discount factor, so it tells you about how we value today as opposed to tomorrow. And so we'd like to be able to estimate those parameters. It turns out that if you work through the mathematics of the economic model, it would imply that the following population moment condition holds. Then involves observed data on consumption growth and asset price and return. Okay, and turns out that this particular function will be orthogonal, so like linearly unrelated to any item that's in the agent's information set at the time that they're making the decision. So again, we get a population moment condition that involves the parameters we're interested in. We can then apply generalized method of moments based on that to come up with estimates. Okay, so what we've talked about so far is to hopefully give you an idea of why generalized method of moments is such a popular method of estimation in econometrics. You see that it's very well, it's tailored exactly to the kind of information that we're getting out of economic models. Okay. Now, what I'd like to do in the rest of the talk is just talk about some other issues that are naturally associated with the method. Okay. First, a few practical issues, very briefly. Secondly, to talk a little bit about information in moment conditions. Implicitly, when we wrote this down, we said if we have a moment condition, any moment condition is kind of good, but of course that's all moment conditions won't be created equal. We need to say a few words about that. Briefly mention some inference procedures that have been developed within this framework that can be employed. And then I thought it might be useful just to mention some of the issues that are being actively researched on this, by econometricians at the moment. So topics on the research frontier to give you an idea of the directions in which this kind of body of work is going in. And then finally, just to mention some additional resources and to recap what's on it's already been put on the web page for the talk. Well, practical issues. Here I'm thinking of, so we've defined our estimator mathematically, but a question of how do you actually get that number if you had the data? Well, of course, we're going to turn the computer on and let the computer do the work for us. In some cases, we can solve analytically, given the mathematical form of the moment condition, and get a sort of closed form representation in terms of the data, which will speed up the computations. In other cases, particularly in nonlinear models, that won't be possible, and the estimate will have to be found by some kind of numerical optimization routine. Okay, and there's on the web page for the talk, there's a link to a toolbox that's been written by a former student of mine to do this kind of estimation in MATLAB, which makes this fairly user-friendly in that you don't have to specify very much, and then the rest of it all is taken care of behind the scenes. Okay, if we've so that with just a few words about how we would get our estimate, we'd also want to think about the properties that those estimates might have. And the way I've sort of tried to organize this discussion is to think about the sort of information content that population moment conditions have about these parameters of interest to us. And clearly the crucial quantity here is these population moment conditions. That's the basis for our estimation. We need to, once we recognize that, a number of questions kind of naturally occur. First of this is, does this population moment condition that I've written down, I deduced like the ones we had in the earlier examples, does that actually provide me with enough information for my estimation to be successful, using that term loosely? Another question that might come is that if having written down a population moment condition, how can I extract the most information from it about the parameters that I'm interested in? And lastly is, well, what's the best choice of moment condition for me to be using? Now, all of these have been addressed in the literature. The first leads us to the issue of identification. The second, within this context, leads us to the question of what's the best choice of weighting matrix. Remember, that was the matrix sitting in the middle of the quadratic form. That is the minimand for a GMM estimation. And then the last thing is referred to as what's the optimal choice of moment condition. So a few words about each of those. To motivate the comments about identification, let's go back to this population moment here. So we have this expectation of the function of Vt and the parameter theta. Now, as I change the value of theta, obviously, I'm going to get a different value for that expectation. So I can think about the behavior of this expectation as a function of theta. Now, what the population moment condition is telling me is that if I evaluate that expectation at theta 0, then I get the value 0, although it's equal to 0. Okay? And that's the information on which my estimation is going to be based. But for the subsequent estimation to be successful, this must represent a unique property of this unknown true parameter value. Okay? It has to be the case that not only is that true for theta 0, but it must not be true for any other value, possible value for these parameters. So that leads us to what we could refer to as an identification condition, is that if I look at this expectation at any other value of theta, it's not equal to 0. So that's a very crucial thing for us, okay? Because in this case, we're starting out with a unique piece of information about this unknown, and then it's going to be possible to estimate it. Now, that's very simple to write down, but it's in practice, that's often a very hard condition to verify. There are cases in particular functional forms for f where you can work something more revealing condition out. An example is linear models, such as in the returns to education example, where, for instance, we would need that quarter of birth, the variable quarter of birth, to be correlated with the number of years of education, which Angus and Kruger argued that it is. But in more general circumstances, it's often more of rather than something you can verify, it's more of a prayer, and you hope that it does hold. In practice, if it doesn't hold, or if it's close to not holding in a loose sense there, you'll discover it as you go to do that estimation. As you turn your computer on and it tries to find a value that minimizes that the GMM miniman, it'll have a very hard time doing it. And that can often be the first inkling that you get that identification is suspect in the model that you're using. Assuming that we've got identification, we could then we'll move on and to our second question, which was saying if I've got a particular moment condition, how can I extract the most information that's possible out of that moment condition? Of course, information about my parameters. Okay? And to motivate, so how we would do that is relating to the question of the particular choice of the weighting matrix that appears in the center of the GMM minimum. And to characterize what will be the optimal choice, we need to just summarize the large sample properties of the GMM estimator. Okay, so that under very standard conditions, the estimator will have a large sample normal distribution. It's centered on the true value, and it's got some variance that we'll call V. Now, if Q is equal to P, Q is the number of moment conditions, P the number of parameters. Okay? If that happens to be the case, then that V doesn't depend on the weighting matrix that appears in the GMM miniman. Reasoning for that being simple, you recall we noted that if P and Q is equal to P, then GMM was the same as the method of moments estimator based on solving the sample moment conditions. So the weighting matrix is playing no role. If we have more moment conditions than parameters, Q is greater than P, then V will in general depend on the weight choice of weighting matrix. Okay? And so we're going to term that the optimal choice of weighting matrix, the one that will extract the most information for us, is the one that minimizes the large sample variance of our estimator. Okay? The one that gives us the most precise estimates. Okay? Now that we can characterize in terms of population values, and it turns out to be the inverse of the population variance of the sample moment. Now, as we step towards implementing that, a few issues come up. So first, W, as you may recall, was the limit of was a limiting value for the weighting matrix. So first practical issue is how can I get a WT that will converge to that limit? So I want a WT that converges to the inverse of that variance. Now, since it's a variance, we know how to consistently estimate variances. Natural thing to do is to come up with a consistent estimate of that variance, take its inverse, and use that as the weighting matrix. That sounds good, but if you pause to think about it, think, wait a minute, isn't there a circularity here? Because usually when we go to construct variance estimators in these kind of settings, we need to have an estimate of the parameters to do it. Right? So there seems to be a circularity that to construct the weighting matrix that I need to get the estimate, I already need an estimate. Okay? But we can resolve that straightforwardly by adopting a multi-step procedure. Okay? And then on that first step, we'll just take some suboptimal choice of weighting matrix. It will deliver a preliminary estimate of theta. That can be used to get our consistent estimate of the variance. And then on the second step, I'll use the inverse of that as the weighting matrix. And that will give me what's referred to as a two-step or second-step GMM estimator. 2 steps are sufficient for it to have the optimal properties, to be the most precise estimates in terms of large sample properties. But in fact, you could carry on iterating this procedure and get something called an iterated estimator. And there's fairly compelling evidence to suggest that there are gains to iteration in terms of finite sample performance of the estimator. The last question that we wanted to highlight here in terms of information in moment conditions was what's the optimal choice of moment condition? So what we were just talking about was, suppose you've given me a moment condition, how can I get the most information out of that? This is now a different question. What I'm asking is, what's the best moment condition to give me? And it turns out that there's a kind of quite a straightforward answer to this, although it won't be very useful for us in the context in which we're working. We're working in the classical paradigm here with generalized method of moments, and within the class of consistent, uniformly asymptotically normal estimators, the best estimator we can use is maximum likelihood. Now, it turns out that we can demonstrate that under fairly mild conditions, maximum likelihood is actually a special case of a generalized method of moments estimation, or in fact of a method of moments estimation for that matter. And the moment condition that you're using, implicit moment condition, is just the score function associated with the distribution. Okay? Thus, obviously, since maximum likelihood is an example of GMM, maximum likelihood is the most, gives us the most precise estimates. The best choice of moment condition is thus the one that's associated with maximum likelihood estimation, which is, as I said, the score function. Now, that's very easy to characterize, to write down, but it turns out not to be very useful for us, because if you think back to the beginning of the talk, when we explained the popularity of GMM, we're saying that what was so nice about it was that it gave us a way of estimating the parameters of our economic model, given the information and the restrictions that we got out of the economic model. Okay? Now, we saw 2 examples of how those restrictions often take the form of population moment conditions, but crucially, neither of those examples actually involved the distribution of the data, telling me exactly what the distribution of the data was. Okay? And that's the same in most other economic models. It doesn't tell us what the distribution of the data is. Okay? So that if I'm going to take this optimal choice, I'm forced into a situation of having to make additional assumptions about the behavior of the economic variables that are unjustified by economic theory. And that's exactly the kind of thing GMM was designed to help me avoid doing. Okay? So whilst we know what the optimal choice is, it turns out not to be feasible in most economic settings. Okay. So there has been some other work done on particular classes of moment condition, such as ones involving cases where errors are unrelated to vectors, which are often called instruments, which both our examples fell into, actually, where people worked out a so-called optimal instrument. But it can be complicated to implement, and you don't see them applied very often in the literature. Okay, so now just turning briefly to some inference procedures. What kind of inference procedures might be interested here? I think there's 3 broad questions that arise in these kind of economic applications. First one, perhaps fundamental in a way, is the model correctly specified? Remember, the population moment condition has been deduced from an underlying economic model, and all our inferences are going to be based on that. So natural first question is that original model, does it appear to be consistent with the data? Is it a good representation of the data? If it passes that kind of question, another thing might be, well, does the model satisfy certain particular restrictions or additional restrictions that I could impose that might tell us something about economic behavior? And lastly, as you know, if you've got 2 economists in the room, you've got 3 opinions. So we have often competing theories, and there's a question of which one is, we might want to work out which model appears to be more consistent with the data. Okay. So all of these questions have been addressed to varying degrees, and collectively they've generated voluminous literature. And the answers all involve hypothesis tests, and they're either based on sample moments or they're based on the parameter estimates. I just mentioned one explicitly, which is called the over-identifying restrictions test, which could be applied to address the first question there, whether the model is correctly specified, in a case where we've got more moment conditions than parameters. Because this statistic is sort of ubiquitously reported in all applications of GMM. This is common within the GMM framework as reporting the value of the log likelihood function is in a maximum likelihood estimation. Well, this test, the reason it's so frequently used is it goes to the very heart of the very crux of GMM. Okay, the method is our estimate is based on the information in the population moment condition. Okay? So what we would like to know is whether the data appears consistent with that information. If we've got more moments than parameters, we have scope for testing that. And there's a very simple statistic that can be used for doing it. It's called the over-identifying restriction test. And it's just the sample size times the second step GMM minimand, or the GMM second step minimand, evaluated at the associated parameter estimate. And under the null hypothesis that the moment condition is consistent with the data, it has a large sample chi-squared distribution. So it's very simple to implement, very simple to calculate, because it's an obvious byproduct of the estimation being based on the minimand. So that's a kind of won't say any more about the inference methods. Maybe with given time, it's an appropriate moment to move on to think about what topics are being actively researched sort of on the frontiers of the subject now in this area. All the kind of to motivate the issues that people are looking at. If you think, so just to mention a few words about this theory. Well, this theory we very briefly reviewed here is we call it large sample theory, or more appropriately, first order asymptotic theory, which of course, where is as results derived by imagining our sample size goes off to infinity. We're never in that situation of having that infinite sample. And so what we're doing is using this theory as an approximation to the finite sample behavior of the statistics. So once we recognize that, natural question is, well, how well does this theory approximate finite sample behavior in the kind of places where we want to apply GMM? And can we identify the kind of factors or aspects of the model specification that appear to affect the quality of this approximation? This has been investigated a lot, both in terms of analytical studies, trying to develop sort of higher order asymptotic theory, and also a lot of simulation-based work, just generating artificial data from structures that would fit our economic theories and seeing how well these methods perform. What can we say has been learned from this? And it's been not surprising. It's a kind of good news, bad news situation. Sometimes it works well, and sometimes it leaves something to be desired. Okay, it doesn't work so well. What factors can we say that have appeared to affect the quality of this approximation? Can we identify features of the model that will flag out for us when it's going to work well and when it won't? Well, talking in very broad terms here, so the functional form of that appears in the moment condition, a functional form of f, that's going to be important. Talking loosely, the more non-linear it is, the likely less well this theory is going to approximate for a given sample size. Another feature that seems to be important is referred to as the degree of over-identification, and that's the q minus p, which is q is the number of moment conditions, p the number of parameters. So it's loosely a number of additional moment conditions that we have beyond the number of parameters. The interrelationship, especially in terms of information content between different elements of the moment condition. And the last one that's also very important is the quality of the identification. We talked about identification earlier on. This is saying whether the moment condition provides us with enough information. Then what people have found out is that in some circumstances of interest, you might think that the result of the identification condition that we wrote down is technically satisfied, but nevertheless, the quality of the information being provided by the parameters about the parameters is not very good. Okay? And if we don't have very good information, this theory is not going to provide a very good approximation. And that's something that actually has been leveled at the example of returns to education, where the moment condition involved, a key aspect of the moment condition was the use of the quarter in which the individuals were born. And people have subsequently questioned the quality of the identification from that type of moment condition in that context, and thus the reliability of the inferences that have been drawn. So how have people responded to this body of evidence, evidence on the behaviour of GMM? Well, there have been three responses: two within the GMM framework and one outside, which I'll come on to in a moment. There's the two broad responses within the GMM framework have been as follows. The first is to say, okay, that I'd like to stick with that first order asymptotic theory that I was talking about before, and what I recognise is that to get that to be a good approximation, that will work with some moments but not with others. So what people have devised is sort of methods of moment selection, and a database that allow you to try and work out which moments are actually contributing information to the parameter estimation and which ones appear not to be adding any information, with the idea that you retain the ones that help and you discard the ones that don't. Okay? That's the first approach. A second approach has been to say, yeah, I don't think that this first order asymptotic theory is such a great idea. I'm going to consider alternative approximations to develop a large sample theory, and try and use that frame, an alternative asymptotic framework, to come up with inference procedures. And leading within that has been what's called weak identification asymptotics, which is where people have looked at the problems caused by poor quality information out of moment conditions. Another way people have done it in refining the asymptotic approximation is used resampling methods, collectively listed here as the bootstrap. So using artificial resampling methods to try and improve the critical points, the accuracy of the critical points used in tests. And the last thing we have here is called many moment condition asymptotics. And this is goes to the issue raised by the when on the previous slide. It said one aspect was the degree of over-identification, Q minus P. If we have many more moment conditions than parameters, it can turn out that the usual asymptotic approximation is not good. So people have developed an alternative theory that's sort of tailored to circumstances where we have a lot of moment conditions, and looked at what insights that can bring. All of those, I think, are being actively researched still. Okay. The last response is actually to sort of step out of the GMM framework and to say that the problems that these studies have encountered are something to do about the structure of a GMM estimation, and have led people to think about alternative ways in which they can exploit the information in moment condition for the estimation of parameters. And the class of estimators that have been looked at a lot now in econometrics is so-called generalized empirical likelihood estimators. That contains things like a continuous updating GMM estimator, empirical likelihood, exponential tilting estimates. And they're just different ways of coming up with estimates based on the information in population moment conditions. And some initial results suggest that they're very promising and may have some advantages over the traditional GMM framework in some settings that are of interest to us. That's pretty much all I wanted to say. I hope I'm about on time. Additional resources. This is also on the webpage. I wrote a book on this, on Generalized Method of Moments, particularly geared towards time series and applications in finance and macroeconomics. This graduate student of mine, Kostas Kyriakoulis, now working at SAS, he has written a toolbox which has a graphical user interface, for those of you familiar with MATLAB, so you basically just put in certain things on a screen and then everything else takes place behind, and it calculates all the kind of statistics that one would usually be interested in. And that's freely available. And it's actually It's based on programs that I used when I was doing the book. It was done afterwards, so the book doesn't mention anything about it, but the help files that he's created, which I think are very good, and the examples that he used are linked back to things that are discussed in the book. And a further resource that is a book of readings that came out back at the end of the last century. It sounds very dramatic, doesn't it? It was back in 1999. But you would find also these days that most econometric textbooks will have at least something about generalized method of moments. There'll be a chapter somewhere about them.